How was the midterm exam? Is it easy, right? Man, it should be easy because the contents are very similar to a couple of years, 3 years ago actually, and the average is usually 85 or 100. But why do you make physical face on me? Just to make it. Well, you know, as I already talked, I really hope you guys fill out your paper. I mean, that is very, very important. Well, this is not the American GRE type of exam. Just put it something so that I can give you partial. That is very important, you know, right? And also, these are the paper, the home exam. My teaching assistant already graded. I will check on it again, and I will give you this one by this Friday. Is there any questions on midterm exam? Yeah, US talks, because that is very, very easy. You don't have any questions, right? You agree with me? Do you agree with me?
I don't have any questions.
Huh? Man, you even didn't listen to me. My question was, any question you have on midterm exam?
I said I don't have any questions.
Yeah, that means the exams are easy.
Not necessarily.
Not necessarily. What do you mean by that? Well, anyway. All right. Well, we before starting the main contents of the CO2 equilibria, I have been in the San Diego a week ago to participate in the American Chemical Society meeting. Well, actually, I was organizing a couple of symposia. Do you know what symposia is? Symposium. Yes, symposium is one conference, right? And symposia is kind of couple of seminar in the environmental chemistry division and also geochemistry division. In the geochemistry division, I have organized the CO2 sequestration in deep sea environments. I just want to sequester CO2 because there are tons of CO2 emitted, right? So if we want to cut down CO2 in huge amount size, we don't have any option, just one option. Put it into the earth or seabed sediments. Well, you guys can say, well, professor, well, we can study and we can research so that we can convert CO2 to very, very good chemical compounds. Well, CO2 is C plus O2, right? So if you can degrade C part and O2 part, well, you can use those two as the basis of useful chemicals. Is it right? What's supposed to be the problem? Were there any scientists, chemists, who want to develop such kind of chemical procedure? Maybe there are tons of scientists who want to develop such kind of chemical process because that can give you money, right? So what's supposed to be the problem? Why 100 years ago, the scientists already developed such kind of chemical process So why the people want to CO2 put it under the ground? Okay.
CO2 make us warmer.
Yeah.
Greenhouse gas. So scientists hate CO2. So put it.
But my question was, well, if you can convert CO2 to useful chemical, they already developed the chemical process to convert, CO2 to useful chemical. Why do they want to do that? Why did they want to do that? I mean, why didn't they? Yeah, well, 100 years ago, they already know how to convert it to CO2 to useful chemical. So why nobody even don't have interest right now?
Cost efficient.
Yes. Converting CO2 to another chemical, at first time you want to break down CO2. CO2 is very, very stable, is it? Well, you can see CO2, everywhere. Even you breathe out CO2. So can it be easily degraded? No way. What you should do to degrade CO2? Man, Tom, what do you want to do to break a CO2?
To break CO2, we need to put in the reaction a huge amount of energy.
Huge amount of what?
Energy.
Energy, right. So how do you want to put energy into CO2 to disintegrate? What's supposed to be the method? Just like that, your palm just to give the blow, hand blow by ancient Chinese have done that all days. Tang Dynasty. Just kidding. Sorry. Well, the easiest way is to use electricity. That's it. Just make some spark, and it can cause high energy, so it can be easily disintegrated. So disintegrate, breaking down those two CO2 part will actually need more energy. You want to convert CO2 to another useful chemical. If you use much more energy, I think that is not good method and option actually. So people think about that at first time because we have humongous amount of the CO2, put it inside the wasted oil well. Oil well, it is very good structure to safely contain CO2. And one thing good for wasted oil well, if you want to at first time you find oil well, if you just put the pipe into the oil well in the ground, you can see the oil actually exploded at first time because of the pressure. But if you can take out 90 or 70% of oil, petroleum, what happens is you need to pumping it out to take out the oil. But if you can, so that the oil, petroleum industry, they have done, injected some inert gas, just like the nitrogen gas, into the oil, and then you can take out oil in oil well. But nowadays, just don't do that. Instead of the nitrogen, you can put the CO2 into the oil well, and then you can take it. So you can sequester CO2, and then you can take oil. That is a very good idea, right? So, anyway, my point is we have discussed a couple of presenters' presentation last Wednesday, and we really had a good time, actually. two of my PhD students actually gave presentation there. Well, the first time, you guys know, it is very stressing, and it is very kind of, not easy moment when you are giving presentation in front of the, world-renowned scientist. Maybe you even, well, if I, ask Tom, invite here and teach this material, Tom may be kind of in stress. But the two students actually really gave good presentation. Well, they really have good exercise before and training before giving presentation. It seems right. They are enjoying giving presentation actually. So that means you guys actually can do that. Even well. In my days, going abroad and then, having PhD, United States or Europe, then we can actually give some kind of my experimental result to all the people, all the scientists in the world. But nowadays, the PhD students in KAIST, they are really, really doing good. So, and also some of them even have job, teaching job, just like the assistant professor, associate professor in the States. So, you students, never ever, limit your capacity. You can do anything if you have dream. That is very, very important. Have dream. Because I think those two students are not very bright. Don't talk to them. But they really have very hard training. Well, they can get over, and they really have good results. Well, maybe next time I will show their presentation. So, video slide. You can see that. And one more important thing is, well, when you give a presentation, the end of presentation, well, if you, maybe at first time, your heartbeat is just like 2,000, per second. Wow, 2,000 per second. Your heart is pumping. Even your tongue is trembling. And never ever use the razor pointer when you start, because it always shaking. So everybody here know, this guy start to trembling. Wow, let's enjoy this. So don't use that. If you focus on your presentation, maybe in 5 minutes, your heartbeat exponentially decreased. Maybe it is just like the 50 beats per minute. It's just like the marathoner can have. And then start the lace pointer. And as time goes by, you can start your presentation. You are just like the David Letterman in his show. You can enjoy your show. And even you can teach the people sitting in the chair. That is very, very important. All right, Amy. The important thing is having dream is very, very important. And also don't limit your capacity. That is very, very important thing. All right. I want to go back to the contents I had done before. We are actually in the CO2 equilibrium. Well, we actually want to estimate the pH of raindrop, the pure raindrop, and also we added NOx, and we added, ammonia is the example of the NOx. And also we added some sulfur dioxide. so that we can actually estimate the pH of the raindrop. Well, think about that. If the God just make the rain, the pH of the rain around the 5.5, what happened there? Is the Earth safe? 5.5 pH, raindrop, just falling down. What happened? The first time, your father, who doesn't have hair, never ever was sparsely having hair, never ever want to go out. And the second, maybe that would be in 100 years, episode. But if the 1,000 years just passed, what happened? You understand my question? You didn't hear, man. Well, you cannot easily find very good rock. Maybe the low acidity erode the rocks. So, if God really have good intention, He should. I'm very sorry. I really don't know. Well, he or she. I'm not being a sexist anyway. Let's say just a he. If he really have a good mind, he maybe you guys can think there should be some kind of buffer material on the Earth. That's it. What could it be? What could be the kind of buffer material against low, acidic raindrop? Think about that. We, human actually can live easily and freely in the neutral environment, pH 7. Well, right? Have you ever tried the 5.5 pH water? Think about that. If you just drink Coca-Cola every day, every night, and what happened? Can you live? It's very difficult, right? So, God made some kind of buffer system. What could it be? What is the most, representative buffer on the Earth? Juntae. Yeah. Well, think about that. We pH 7 is, we want actually. But important thing is the raindrop is 5.5 actually. So it's still always, there is just a 5.5, and the Earth actually becomes the 5.5, right? So it should be something, to buffer or to protect. Man, I just give you one. All right.
I've learned in another course that the ions in the rocks acted as a buffer.
Yep.
Calcium or magnesium ion.
So calcium, you use the calcium? I think, would be, this could be the most, highest buffer actually, hydroxide. Right? The pK is around 10 to minus 12 actually. So that means the pH is around the 12. So you guys don't think this one could be the average material against this one, right? Because this is around 12. What about this? This one could be around the 9 point or 10 point something. So, well, simply think about that. 7, well actually 1.5, 8.5, right? Well, this is not that, right, calculation, but estimation, as a scientist. Well, so this chemical species could be kind of buffer chemical species. So it cannot be digested as a solid. So there always should be with cation, just like the Ca, or calcium, or sodium, or iron, like that. So all of these can stay as a solid stone, rock, right? So if rains with acidic rain, and this solid on the earth with pH 8.5 higher can mix, and then you can have neutral environment. But problem is, if human contaminates the earth with the sulfur, SO2, or NOx, well, the pH can decrease actually. So, the environment is not safe. All right. Here, we added pure rainwater, and we added sulfur dioxide, and we added ammonia, and finally we can have 5.66 here. And talk about the surface water. Here, what is the pH of the water in Indiana limestone quarry? Well, we call it quarry and quarry. We'll actually think about the limestone quarry. Well, the people actually take out some good limestone, and there may be limestone around here, CaCO3, and then the rainwater actually drop down here, and the acidic rainwater with this calcium carbonate, red actually. 웬만하면 커피 좀 가지고 오지. 커피 좀 줘.
네.
자, 내가 다 이야기할게. 여러분, 만약에 졸리고 힘들면 오지 마세요. Don't come here. 왜 와? 내가 그때 이야기했던 것 같은데, 여러분하고 나하고 지금 쇼를 갖다 즐기는 그런 상황일 것 같은데, 여러분은 자. 그치? 내가 이야기를 하는데, 그건 굉장히 루드한 거야, 내가 볼 때는. 내가 이야기했지만, 그냥 책 지금 기철이가 읽고 있는 거 읽으면 여러분 다 공부돼. 그러니까 졸리거나 다른 중요한 일이 있거나 숙제를 할 일이 있으면 오지 마요. 왜 자기 자신을 갖다가 그렇게 이렇게 깎아먹는 행동을 갖다 하는지 난 이해가 안 가. 이해가 안 나? 그렇게 살지 마세요. 고등학교 때까지 그렇게 살았으면 적어도 대학교 와서는 좀 학생답게 좀 공부할 거가 있으면 공부를 하고, 자기가 그거 매니지가 안 되나? 오케이. Alright. Well, if you really think my class is not interesting, well, don't come here. Okay. So we just want to know the pH of water, actually here, on the limestone quarry. So how do we set up equations to estimate, calculate the pH of the water in the limestone quarry? Well, the first time, we just want to know the equilibrium equation here, chemical equation. So calcium carbonate actually dissolved in water calcium ion, which is divalent 2+, and then it can dissolve into the carbonate ion, which is 2 minus. As you guys know, calcium carbonate is solid, and in the equilibrium, well, we can set up this solubility product constant. Because KSP is, well, all of the K is equilibrium constant. Whatever it is, K could be the reactant and the product. Here, CaSO4, the activity of CaSO4 solid, pure solid, is actually 1. So you don't have to care about this solid part. So solubility product always shows the concentration product with products, actually. So we call it solubility product. All right? So KSP, well, as I already taught, the old scientists already, calculated for you guys. And it just the value is 10 to minus 8.42, and which is the product of 2 products. Here, KSP is very significant in the system. Well, the problem is if the calcium carbonate is fully dissolved, KSP actually cannot be counted. There should be solid in the system. This is very, very important. So at the equilibrium, there always should be CaCO3, solid exist. And part of this solid dissolve Ca2 plus and CO2 minus. In this equilibrium system, this KSP value actually has meaning. All right? Then, using, well, just remember the whole, equation previously, in the NOx and SOx cases, and then set up the charge balance, because we have calcium 2 plus here at the proton part. I mean, plus part, you have proton, and also you have calcium ion 2. And then we can put the whole bunch of the minus anions here, bicarbonate and also hydroxide. Because calcium is bivalent and carbonate is divalent, you can put the 2 in front of the concentration. All right, and then as we did the same way, we just substitute all of the items with H. Here, this one actually, CO3 2 minus can be related like this. And then using KSP equation, you can have C2 plus equals 10 to 13 times H square. And then substitute all items with the the previous equilibrium equation, and you can put it all of this. And also, we want to briefly calculate. Let's just assume the rate pH is pH 7, and then put it the concentration. And then look at here at the left side, 10 to minus 7 and 10 to minus 0.5. Which one is bigger? Tom?
Of course, 10 to minus 0.5.
Yes. This one is 0.000000 something, and this one is almost the 1 point something like that. So this can be removed. Here, 7.3 and 7.0 can be removed. So these two are significant. So at first charge balance equation, this one actually remained, and this one also remained. That means calcium bicarbonate is the dominant chemical species actually in this category, right? 11시인데 잠이 와. 아우, 참 대단하다, 다들. 뭔가 좀 더 재밌는 그런 방법이 있을까? Michael, what do you think about this? Why the student just falling asleep when I start to teach?
Maybe they watched dramas last night.
They drink last night, whole night?
No, watched dramas.
Did you do that, William?
No, I just woke up really early.
You, take it.
공부를 했다고 하면 아무도 안 믿겠지만, 네, 제가 무슨 바람이 불었는지는 모르겠지만 그런 공부가 너무 재밌어서.
Well, that can be excused. All right. If possible, as Michael did, he just bring a cup of coffee over there. I let them know that is coffee or not. Maybe vodka. Well, you know, bring some and please be awakened. All right. And I will do my best. Okay, so here we have hydrogen. Proton is not that significant because the pH is around the maybe 7 or 6 or 8, right? Because 5.5 plus. Well, think about it. I just asked my master student in my research group. And here is 1.5 liter of 5.5 pH solution plus. Here we have 1.2 liter of pH, let's say 9.5 solution. If we mix these two, what is the pH of the solution? Well, how do you calculate this? Do you want to calculate 5.5 plus 9.5 divided by 2 equals the pH? Or?
The volume is different, so.
Or do you want to put more, give some credits on the amount because it is 1.5 liter and this one 1.2 liter? The volume is a little bit more, right? So let's say this is 4 and this is 2. So in this case, you want to multiply 2 and multiply 1 and plus and divide it by 2. Does it give you the right pH? Kenyon, what do you think about this?
Don't you find the number of moles with concentration? Well, you find the concentration by using pH, like the molar concentration, and then you multiply by the volume.
Right. If so, molar concentration of what?
Pardon?
Molar. You just mentioned molar concentration, right? So molar concentration of what?
H plus.
H plus. Let's say here is 0.5 millimolar, and here you have hydroxide. Let's say 0.1 millimolar. So how do you calculate this?
From the concentration of hydroxide, you get the concentration of H plus. The value of pH is 9.5.
Let's say, yeah, she literally has good, micro. So
What is the concentration?
micro. Well,
Of
actually,
what?
I don't want to, exact calculation. Could you just give me a brief calculation procedure? How do you want to calculate this?
Well, if you have the concentration in moles per liter, you multiply by the volume, and you get the number of moles, and you add the number of moles, and then divide by the total.
All right, thank you. Fair enough. That is my master student's answer actually. Volume is important. Well, volume is important, right? So that means if I give you a question, maybe as a final exam, what is the pH of these two decimal case? I just give you how to calculate pH rate. So calculating pH relate to what? The concentration of a whole bunch of different chemical species in solution, right? So this is very, very important. So at first time, what you should do is just find out what kind of equilibrium chemical equation you can have in solution. This one and this one. And then what you should do is you can set up equilibrium equation, right? For the carbonate, hydrogen, bicarbonate, ammonia, and NOx, SOx, everything. And then you can set up the using equilibrium constant. You can set up the equation. And then what you should do is you can set up charge balance equation, which is mass balance equation. And then you can convert for concentration with equilibrium equation with hydrogen ion concentration. Then you can convert, you can calculate the concentration of hydrogen ion, which is the pH of the solution. You understand? Got that?
So you mean that we don't have enough information to calculate the pH on that problem?
Well, if I give you the question, I will definitely give you a whole bunch of information which related to K value, K and some kind of chemical equations, and then you can set up like this, and finally you can calculate H plus. So now you guys can understand how to calculate the pH. Well, as you later, my master student, at first time they just enter my laboratory. I just asked them, solve this. If you can, go back. Well, I think I'm middle school chemistry. Well, they may actually calculate like this. Molar concentration and volume, you may, calculate like this. But the real one is you need to set up this procedure and then calculate, substitute, and then you can actually predict the pH of the solution. Well, think about that. Well, we add actually gas, right? If this one is gas, and then we just bubbled all of this gas, what's the difference? Or there is gas, if you just pour the water and then make gas dissolving solution and then mix it together, what's the difference? Nothing, actually. All the same. So never ever forget the procedure, how to calculate. That is very, very important. All right? Well, anyway. So here we can actually make the equation very brief, and then we can calculate H plus value. So as I already taught, this side calcium exists, this side bicarbonate exists at that pH. So you guys can actually calculate the pH of that water on the quarry is around the 8.24. Wow. So think about that. The pH of water is around the 5.5, right? Now the Korea water actually 8 point, something. So you guys can now estimate acidic, a little bit acidic, right? And a little bit basic. This is acid, right? And, well, sulfuric acid is acid, right? And NaOH, sodium hydroxide. This is base, right? Okay, so a little bit basic ground and a little bit acidic, rainwater. It can be mixed, and we can have relatively, neutral environment. Well, sometimes it could be a little bit different. The soil, could be very acidic. I have usually take some samples, KAIST soil around the North Gate. The pH of the soil is around the 3.4, I think. I really don't know. There should be some kind of very acidic soil minerals in there, and it would be very, very acidic. But sometimes you can have very basic, pH of the raindrop actually. In that case, well, you can have neutral. Or acidic, acid rain and acidic soil, well, you definitely need to move actually. As I would like to, what's the difference between plants and animal? Why animal is so, better than plants? Develop organism.
Animal moving.
Yes, that is. If you can find some hazards, or if you can find some not good thing, as an animal, you can move. But plants, they cannot move. What should they do?
Adapt.
Yes. Or
Die.
So that is the reason why the animal is much higher, organism on the earth. Well, anyway, think about it. If the plants can move, it is kind of SF, science fiction drama. Anyway. All right. Well, this is all for the chapter 4 for the acid rain case. Next time we will talk about the fate and transport of contaminants. This is very, very important. Well, as an environmental scientist or environmental engineer, fate estimation is very, very important. Your fate is doomed. What should you do? Maybe go back to your dormitory and lie on bed and try to wait. What is fate like? Michael? Fate?
I think it's what is determined by ourselves.
By yourself. Wow, that is very big. Most of the people, students, whenever I ask fate, they always mention about the God. So fate is not by people, humankind itself, and actually by the God actually. But I'm not talking about God. But we are talking about the fate of contaminants, which is very, very important. Why do you want to know the fate of contaminants? Tom?
Phase of contaminants. Because the phase of contaminants, that is an index that can reflect how long the contaminants can get to this status and how much it exists till the end.
Right, because we can actually do the engineering. That is very, very important. Whenever you are questioned by the people, development is really, really, environmental destruction. You think so? Do you think setting up the new construction in the middle of the river, is it actually environmental destruction? Quite agree. Well, as an environmental scientist, you may say, well, that could be. But as an environmental engineer, you cannot say it is construction, it is a destruction, I think. All right, well, anyway, as an environmental engineer, the fate is very, very important because, think about that. Contaminants are your enemy. So if you know the fates of your enemy, well, you can manage those enemies well. If you don't know them, you cannot do it, actually. So what's supposed to be the fate of the contaminants? Think about that. Well, there is a very wonderful, I'll just give you one. This is tetrachloroethylene, which is carcinogenic chemical compounds, because this is very famous. Because what's that? There are these contaminants actually so harmfully affect. There are so many people who can affected by this chemical. It can cause leukemia. It can cause very significant, cancer in the United States. It is 1,000, cases actually popped up due to this chemical. You guys know Julia Roberts, Erin Brockovich, right? At the movie, actually, Julia Roberts fought against this chemical. Well, as an environmental engineer, because these are fire, so we want to actually stabilize this one, right? So what you should do is just to take out this chlorine. And you may think these chlorines may be much more stable, right? And then finally, we have Cl. Right? So you can actually remove one by one. So you may think the toxicity of these chemical compounds decrease because you are cutting out these fires, right? But the problem is the toxicity of the chemical actually increase. So if the soil here fully contaminated with this chemical, what you want to do is you just add electron reduction so that you can easily cut down these chemicals. The problem is, if you don't know the full fate of this chemical, what you are doing is you are actually producing much more toxic chemicals, actually. So this is there are many cases, the environmental engineer who doesn't care about the full fate of this chemical, they just put the reactant under the ground. Because when they measure these chemical contaminants, the concentration of this chemical compound actually decreased. The problem is, this chemical concentration actually increased. So these can kill you. This can kill the people, actually. So this is the reason why we want to know the physical and chemical fate of the contaminants. So we actually want to know the daughter products of this chemical reaction. So next class, we will talk about some physical and chemical fate of the contaminants, which should be very, very interesting for the prepared students, which can be kind of nightmare or sleeping pill for the unprepared students. I hope you guys are fully prepared and enjoy my show. And don't come here if you kind of think I'm very tired, and if you don't, if you're very busy. All right, I think this is for today. And you guys have any question, comments? Okay, take it.
KAIST를 그냥 한국말로 하면 어떻게 되죠?
가장 쉽게 한번 이야기해봐. 뭐 이거 하니?
생애?
너 쉽게 얘기하면 운명이지. 칵테일런트의 운명. 근데 이제 폴춘하고 이제 비슷하게 폴춘. 그러니까 근데 이제 두 가지는 아니에요. 물리적인 목적하고 이제 과학적인 측면이 있는데, 물리적인 측면은 배울 것이고 이미 배우고 과학적인 측면도 배우게 됐어요.
그러면 배웠던 레지던스 타임 이펙트에 속하는.
그러니까 이제 그 레지던스 타임이 중요한 거지. 만약에 여기서 이제 이놈을 끊어버리게 되면 정말 스테이블한 이걸로 가게 되는데, 인브라멘탈 엔지니어로서 그러니까 리덕턴트의 양을 갖다 아끼고 싶은 마음에 여기까지만 보내면 이제 그러니까 정말 이제 난리 나는 거지. 이거는 요거는 이 칼시노젠 이 발암 물질 등급이 예를 들어서 인 것 같기도 한데, 이것 때문에 이게 암에 걸릴 것 같기도 하다. 에린 브로코비치에 나온 걸 보면 줄리아 로버츠가 사실 아주 뭐라고 해야 될까, 스마트한 사람도 아니고 굉장히 일하기 싫어하는 여자 비서로 나오는데, 네? 근데 이제 자기 주변에 있는 친척인가 아마 하여튼 이것 때문에 이제 소송에 휘말리게 되죠. 소송에 휘말리게 되는데, 거기는 이제 저지도 이제 하는 이야기가, 요 컴파운드 같으면 당신이 이길 것 같은데 이거는 아직까지 모른다 이거죠. 이거는 죽을 수도 있고 안 죽을 수도 있고 그렇다고. 그래서 이게 프로볼 칼시노젠이 되겠고, 이거는 클래스 1A 칼시노젠이에요. 그래서 이제 예를 들어가지고 이제 내가 MP를 갖다 한 5개 정도 가지고 있는데, 딱 까가지고 여러분 코에다가 딱 들으면 여러분 바로 죽어. 바로 죽지 않겠지. 한 일주일 후 되면 이제 몸에 몸이 말라가면서 이제 백혈병 징조가 보이겠죠. 여러분 모두 선생은 지금 많이 살고 있었어요. 지금. Any question? 오케이. 다시 얘기하는데 졸리면 오지 마세요. 그리고 여기서 다른 숙제할 것 같으면 오지 마. 그리고 핸드폰이 참 그래. 뭐 핸드폰 가지고 있대 강의 이걸 갖다가 메모한다고 하면 할 말 없는데, 그것도 보시고 여러분 같이 즐길 수 있는 수업이 됐으면 좋겠습니다.